Hello, everyone. The topic today I'm going to present is the development of a quasi-time stretch technology for a indoor positioning system based on pulse-modulated ultra-high frequency radio. The ultra-high frequency radio is in range of 30 megahertz to 3 gigahertz, and the purpose of this module, developed module, is to stretch the high frequency into low frequency that it does not affect the timing information of these signals, and to achieve a high accuracy in positioning. Overview of this presentation. Firstly, we will go to the motivation of this project, ongoing project, and after that, I will talk about a little bit about the ongoing indoor positioning system, and it is a distributed. It is applied to an indoor environment, and the positioning is determined by the distributed anchor reference nodes. And the third section, I will go into the design, the hardware design itself of this stretch module. Then, in conclusion, in the end, the motivation. As I said, this module is applied to an indoor positioning system that based on ultra-high frequency signal, and to achieve a high accuracy, our initial aim is to achieve a sub-millimeter precision. So it is quite a challenging task, and to achieve that, we have to extract the exact high accuracy time resolution, and this can be done by a stretch module. I will discuss about that later. A example prototype system integration looks like this. Some receivers are located at some known positions in an indoor environment, and it just looks like a this system is to locate the position of a transmitter as displays here. Okay, there's a transmitter there. In the prototype, we implement the transmitter using a SDR, is software-defined radio. You can manipulate this radio by using any kind of modulation scheme, and this platform can can implement a wireless communication system in frequency range from 70 megahertz to 6 gigahertz. So it covers our interested frequency range. And in the ongoing project, a radio frequency front end is developed to implement this stretch function, and all the received signals, arriving signal at the reference nodes, they are actually frequency radio receivers, are centralized thanks to the radio to the receivers, and the processing will be centralized on the FPGA. Or you can also simply forward the data into PC and do processing on the PC. On the workstations. The simplified block diagram of this system, it looks like there would be one or multiple transmitters from the left side, the yellow, and it is a SDR platform. And on the receiver side, there are multiple receivers. There is a minimum. There will be minimum 4 receivers are required to determine a 3-dimension position of the transmitter. And a ADC block after that, I think ADC is used for every sensors applications, and for a ADC, this ADC we use in our application is a 8-channel ADCs with maximum 250 megasamples per second of 14 bits resolution. And the signal pattern we are sending, it is a pulse modulated high frequency signal, looks like as depicted on the picture. And this system is a kind of hyperbolic positioning system, and it's different from a like GPS. GPS it determines the position of a of the GPS receiver by detecting the difference from the receiver to satellite, and the intersection of 3 spherical surfaces will determine the position. But in this system, it detects the time difference between a pairwise receivers. So each time difference of arriving information will determine a hyperbolic interface, and the intersection of the 3 hyperbolic interface will determine a unique position of the transmitter. And the signal processing procedure, as I said, there are minimum 4 receivers are used in this application. And the time difference between pairwise, you can a pairwise receiver can be receiver 1 to receiver 2, receiver 1 to receiver 3, and yeah, analog. And the main algorithms in this signal processing procedure, it is a TDOA estimation and the hyperbolic positioning algorithms. As I say, the aim of this application is to achieve a high accuracy in sub-millimeter accuracy. So how we can achieve this challenging target? The key is the processing speed. We have to extract the time information with a resolution in high resolution in 3 picoseconds. That's due to the transmission speed or propagation speed of a radio frequency. And for example, a 1 millimeter accuracy that required a 3 picoseconds in time. Obviously, this is without any interpolation algorithm. Without we don't this is don't assume the noise or some other interruptions, multipulse effect that is ignored for this moment. And yeah, but we have to consider that later. That will be processed by the signal processing phase. And the frequency we are using is in ultra high frequency range, that will be in gigahertz. So that means, according to classic sampling theory, we need multiple gigasamples ADC. That would be either quite expensive or unavailable yet. So we have to find out an alternative way to deal with this issue. A possible solution is to slow down the high-speed signal. How to do that is to implement a sub-mixer architecture, undersampling architecture. What that means, this receiver will be sampling the signal quite slower or quite lower than the bandwidth of the ADC will be quite small than the signal bandwidth. And how we keep the time information using a slow ADC, that depends on the signal pattern. As I said, our transmitter are transmitting a periodic wavelet. The wavelet is a pulse modulated ultra high frequency signal. And we can transmit n wavelets and sample each wavelet take one sample from each wavelet and sampling the continuous n wavelets and to rebuild one period signal. In this manner, we will keep the timing information and do correlation between each received signals. We can derive the TDOA signal and to determine the 3D information of the target. And the key component is one key component is a pulse generator. Pulse generator is used at the gate circuits to turn the ADC on and off to capture the potential level of the signal. And this use a SDR step recovery diode and delay lines to implement this function. And this is generated pulses with 100 picosecond pulse width. And this is sampling bridge that it corresponds to a hold and sample and hold function in ADC. And this is the result of the stretch function. A signal in frequency 1.5 gigahertz are stretched to 0.2 megahertz is more than 6,000 times stretched. This stretch rate depends on the repetition rate of the wavelets and the repetition rate of the sampling pulses. Okay. This presentation goes through a brief introduction of the ongoing positioning system and the circuit. Unfortunately, I don't have much time to explain the details of the quasi-time circuit and the examples simulation result of is presented. Yeah. Thank you.